Hello world, my name is Viktor Engelmann, and in this video I want to explain to you how cloud computing works. Cloud computing is a pretty hot topic right now. There's a lot of videos about that topic, and in such a situation when there are already a lot of videos about a topic, that would normally mean that I would say, okay, I don't need to make a video of my own on that topic, but in the case of cloud computing, all the videos that I've seen are really not that good, and that's why I'm making this video here, because all the videos I've seen, they don't really explain how cloud computing works. Okay, they might show you this or that tool that you can use to create something that can run on a cloud, but they don't explain how the cloud itself works under all of that. Okay, so that's what I want to explain now. I guess you already know cloud computing means that you have several computers. Okay, these are my computers here. In the realm of cloud computing, they are called nodes. And let's say these here are the network interfaces. Okay. So at the very core of cloud computing, you have a container engine. For example, Docker or Cryo. I think there are also other container engines, but anyhow. So the way a container engine works, you can imagine that very much like a virtual machine, although technically it's not a virtual machine. So a virtual machine would really emulate a full separate computer, and that separate computer would run its own operating system with its own kernel and its own programs. And a container engine works a bit differently because they are more like a process running directly on the computer, but that would be an absolute security nightmare. Okay, so if you would just download some software from Docker Hub or wherever and run it, it might really damage your computer. And that's actually the brilliance of cloud engines like Docker, because they use a lot of features to lock this process into a very isolated environment. So I think, for example, they use change root, so that from the perspective of the container, all the files outside of the container don't even exist. And there's a lot of other things, like they use namespaces and C groups, so that the processes cannot communicate with each other. They cannot communicate with other processes on the computer. So it really isolates these processes so much that it is as if they were running in a separate computer in a virtual machine. Okay, I think they even use something like FireJail or something like that, so that these processes cannot even do any system calls to open files or open network connections. The cloud engine even captures these system calls and then can redirect the system calls. Okay, so for example, when this container here wants to talk to this container down here, then the computer, the container engine might capture the attempt to open a network connection. See, you are trying to communicate with this container, and then it might redirect the connection there, so that it doesn't even get out of the computer into the actual network. Okay, So that's container engines. Now something very common with cloud computing is that you have separate networks for groups of these containers. Okay, so technically you can do that using VPNs, virtual private networks. I think you could, for example, use WireGuard for that. I think that would be a pretty good idea. And now the container engine can now capture any connection attempt from one of the containers and say, okay, this container is in this VPN, number one. So anything that this container tries to send out, I'm not sending out directly into my network. Okay, let's say here's a network switch, a physical network switch. So the container engine might prevent the container from sending data out into the physical network. It can capture the traffic and just redirect it, of course, physically through that switch, but logically can then go to this VPN server, and I don't know, maybe this container is also connected to that VPN server. So then these two can communicate with each other. Okay, and this is already a huge part of cloud computing, that you have these very isolated processes which often, not necessarily, but often communicate through VPNs, so that you can control which container can communicate with which other container, which container can communicate with the outside world, and so on. The container itself might just run Nginx, so a web server or a database server, or I don't know. I mean, in principle, anything can run inside a container. So just think of them as arbitrary, very isolated processes that are so isolated you can almost think of them as virtual machines. And if they have to communicate with each other, they communicate through TCP/IP with each other, because the idea is that you should be able to move them to a different computer without any problems. And if you put a container on a different computer, you just reconfigure the network a little bit, and then everything will behave exactly as before. One important aspect of containers is that they contain all the files, all the libraries, all the configuration files that the containerized application needs. So one effect of that is that you can just take a container and copy it to multiple other computers and run them all in parallel. And then you just put a load balancer in front of them, so that now all of a sudden you can serve many more clients than before. And like this, you can scale your application very well. Okay. As I said, that's already a huge part of cloud computing. The container engine really does the heavy lifting. But in reality, you have a problem, because in reality, we are talking about situations where you might have Google or Amazon, companies that have hundreds of thousands of servers, and you don't want to control each and every one of these servers separately. You don't want to tell this server, hey, I want you to run this container. Hey, you server down here, you run this container. Okay. So what you do then is you have another computer here, and that could be called a master node, or also a CP, a control plane. These are so-called worker nodes. Okay, And yeah, now you control all this stuff that's going on here through this master node, okay? And yeah, as I said, this container engine might be Docker or Cryo. And yeah, this master node can be Kubernetes, or there are also other solutions for that. But the important thing now is that all these worker nodes get two processors. One is the kubelet process, and one is the kube proxy. And they communicate with this master node. And now you can control all these worker nodes from the master node. And you can do something like, you can say, hey, I want to run 5 instances of engine X. Okay, or whatever. I mean, there's a lot of things that you might want to run. And yeah, the master node then does some scheduling and says, okay, these 2 worker nodes here, they don't have that much load right now, so it might say, hey, I will put 2 of these instances here, 2 of these instances here, and 1 instance here, or something like that. Okay, and yeah, that's really the thing that the master node contributes to this whole thing, this scheduling, and yeah, that it controls the other nodes. Okay, so it will send a command to these nodes telling them, hey, I want you to run, or I want you to execute the command, something like docker run engine X, and then the worker node can see, hey, I've never seen engine X. I will go to Docker Hub and download it from there, which is a repository where you will find a lot of these container images. And yeah, if one of these worker nodes doesn't have an image for one of these containers, it will typically download it from Docker Hub. And the other thing I've told you about here, this kube proxy, that's a different object with which Kubernetes can communicate. And this thing controls virtual network interfaces. So you will have bridged computing. So then you can have these virtual network interfaces, and you can connect your containers to separate virtual interfaces, and then you can connect these virtual interfaces to separate VPNs. Okay, so then this container might not be able to communicate with this container because they are in separate VPNs. Okay, so the question that now still remains is, how does this communication between the master node and the worker nodes works? And yeah, I gotta say, that's actually quite over-engineered in my opinion, and also overhyped, because what this in the end really does is, I mean, this goes through a network connection, right? And you can only send raw data over a network connection. And yeah, the raw data that these things typically send, I mean, it can send any data if it wants to, but yeah, depending on what containers you're running, yeah, a container might run an FTP server, and then you can communicate with that through the FTP protocol, for example. So there's no requirement for these things to have any specific protocol, but one specific protocol that you will see all the time in cloud computing, especially in the communication between the different nodes is this microservice communication. And yeah, that's a big word, but it's actually not that complicated. So, so to go into that, we first need to talk about the hypertext transfer protocol, HTTP. So the HTTP protocol, you probably know that, but whenever you open a website in your web browser, then the connection between your web browser and the server goes over the HTTP protocol. So, for example, I have here a little HTTP server running on one of my Raspberry Pis, RPI multimedia, and yeah, I can access that using HTTP ://RPI multimedia, and if I want to, I can also add the port. Port 80 is the default port for HTTP, and yeah, so this is the website that I'm getting now. You can press Ctrl U to show the source code of that website. Okay, so this is the raw data that's coming from the web server, and the browser renders this to this page. Okay. Now, yeah, the HTTP protocol, really down on the wire, is a rather simple protocol. So, if we want to, we can connect to this web server manually. RPI multimedia port 80, and in here I can now send the request get/http/1.1 and host RPI multimedia, and one empty line after that. And yeah, this is now the raw data that the server sends back. This is the main thing that it sends. It sends HTTP/1.1. 200 is the status code for OK. It's running Nginx, and yeah, some other stuff in here, like the type of the result, and yeah, in particular, this here is the raw data of the web page that's the content of the index.html file, but I don't want to go too deep into that. The important thing that I wanted to show you is that an HTTP request looks like this. You have a verb like get, then you put a path. So you specify a path to a resource that you want to access, and then you have this HTTP/1.1. Yeah, it's very common to use 1.1. This hasn't changed in forever, so anyhow. And then you have some additional header data, and yeah, a GET request doesn't have any body data, so so after this empty line, the server doesn't expect anything more and then sends its result. Okay, and as I said, GET is a so-called verb, and yeah, there are a lot more verbs, not so many, but yeah, here on this Wikipedia page of the HTTP protocol, you have this list of request methods, and yeah, there's, for example, the most common one, the GET method. POST is also very common. When you fill out a form on a website and can click submit also, then a POST method is used. And then there are some other things that are not that common, like put could be used to send a file to the server. Delete could be used to delete a file from the server. But that, of course, requires some form of authentication. So, yeah, these things are not so common. But anyhow, these are the verbs or request methods, and these are the ones that you can use here in the front. Then you need to specify a path that you want to access, then this HTTP/1.1, and then maybe some header data depending on what you are trying to get. Okay, and yeah, microservices use the exact same protocol. So in my opinion, that's not the best choice because the protocol is not really designed for that. But yeah, here's one example of a microservice that I've written in C++, where I'm using the JSON library by N. Lohmann and the CPP HTTP library. And yeah, this is a pretty simple microservice. It creates a server, then tells it to listen on port 8080, and yeah, in between it's waiting for post requests, you know, this post requests, and when it gets a post request, it takes the data from the body, then parses that body as a JSON object, and yeah, then just iterates over these over the values in that JSON object and adds them up to a result and then sends the result back. Okay, so for example, you can send this data to the server. So post and HTTP/1.1, that's clear. And yeah, this path is the thing that I've specified here. So I could also have another path, like instead of plus, I could also have minus, for example, and then subtract values or whatever. But importantly, you can have multiple of these paths, and the server can look for multiple of these, and then you can select which of these things you want to talk to using this path here. Okay, and this request then tells the server, hey, the data that I'm giving you is a JSON document, and it has length 11, and this here is then the JSON object. Okay, this is a valid JSON object, a list with the numeric contents of 1, 2, 3, 4, 5, and this has 11 bytes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, and yeah, let's try this. So I could run the server here. Okay, so the server is now listening, and in a second shell I could now send this plus txt, so this text here, through netcat to the server. Okay, now it's telling me bad request, and so it rejected this input, but that's a relatively simple problem. You see the HTTP protocol, and yeah, I don't like this about the HTTP protocol, but the HTTP protocol requires line endings to be the MS-DOS line endings, with carriage return line feed instead of just line feed as it's common in the Linux world or the Unix world. And yeah, this Z command here can translate between this Linux world and the MS-DOS world. I'll make this a bit larger. So what it does is it's trying to replace the line ending with a carriage return, and that at the end of a line, that then appends a line feed automatically. So if I replace a line ending with a carriage return, and then that automatically puts a line feed behind that, then you have carriage return line feed. Okay, so if I do that, I can now do something like make CRLF, and now what you see is instead of this error 400 bad request, I now have status code 200, which again is okay. And yeah, this is a bit hard to spot, but it's here at the beginning of this new line here, we have the result 15. Okay, and yeah, this is really what we expect, because 5 plus 4 is 9, plus 3 is 12, plus 2 is 14, plus 1 is 15. So 15 is the correct result for a request to add all these things up. Okay, so yeah, this is really the thing that I wanted to show you here, that microservices really just operate on the HTTP protocol, and they aren't magic either. You have an HTTP server that waits for requests on certain paths, and then using this JSON library here parses the body of the request, and then can process it, send a result, and there you go. That's all it needs to do. Okay, and this is really the stuff that's going on the wire here. So so the master node will encode its instructions in such a JSON way, and then send that with such an HTTP header over there. And yeah, then the nodes over there can react to that. And yeah, when you are communicating with the master from the outside, for example, with a program kubectl, for example, then kubectl also uses such requests to communicate with Kubernetes. It actually doesn't even do that directly. Kubectl actually internally just calls curl, and then curl does these things. Okay, but okay, anyhow. Now, in my opinion, that's really a bit overhyped, because if you look at this communication protocol that everything uses, I mean, that's just sending strings back and forth, okay? And yeah, the payload is encoded as JSON, and okay, that's a good thing, because yeah, JSON is a pretty well-known format, and there are a lot of tools around JSON. And in particular, there are JSON schemas, which are description files that can describe legal JSON objects. That's a well-known mechanism in the JSON world, that you write a JSON schema, and then when you get some JSON data, you can then just compare that JSON data to that schema. And if it matches, then you know that you have all the fields that you require, and the fields might have some restrictions on the texts in there, for example. So although this is not exactly an object-oriented way of passing data back and forth, it comes close, okay? And yeah, as I said, these JSON things can be specified with JSON schemas. And this is where OpenAPI comes in. This is a file specification, which is relatively good. So you have this YAML-based file type. I think you can also use JSON if you want to. And with this file type, you can really specify all the kinds of requests that you will accept and what you will send back in response. So this makes it not exactly an object-oriented interface, but it comes close to an object-oriented interface. And yeah, this Swagger is really the glue between these two things, you know, between your maybe object-oriented programming language on the one hand and this really text-based communication protocol on the other hand. And yeah, I think these files are quite larger than I would like them to be. But yeah, the main things that you will see in these API specifications is a list of these paths. Okay, so here you would have, for example, a path /pet. In our example before, we might put a /+ there. Then for each of these paths that you offer, you know, here is pet, there's pet find by status, pet find by tags. So all these paths, and for each of them, you specify the HTTP methods that you will accept. Like here, this one will accept a post request, a put request, find by status will accept a get request, and so on. And yeah, post request here then defines the parameters that it expects and where they should be taken from. So for example here, the parameter is taken from the body, and this parameter is required. And this here, $ref, is like a class definition, okay? And yeah, this is a JSON schema you reference here, but a JSON schema, as I said, is similar to a class definition. So that's why I say this comes close to an object-oriented communication protocol. Yeah, this schema here references the class /definitions/pet, and that's all the way down here, far down here. You know, you have all these paths with the methods and the parameters. This is really just a huge list of all the paths and methods and parameters that you allow. And yeah, down here, definitions, you know, I said here, reference definitions pet. And down here we have definitions pet. So this is a class definition that was referenced in that pet path. Okay, and this is very much a class definition where you have an attribute named ID, which is an integer type. So when you transmit it, it doesn't have to be put in quotes, and it is required to satisfy the int64 schema. And yeah, this pet class also has another property called category, which is an object of type definitions category. So definitions category, this is a type for that object, and so on. Yeah, you have a name of type string, and you can give examples which are then used in this preview over here, but now, although I think that this API specification is very large, you know, there are a lot of lines involved to specify your API. Yeah, it's still a very good thing because there are a lot of tools out there which can work with these open API specifications. And one example is this openapi-generator.tech. And in here you can go to Getting Started CLI installation, which will show you several ways to install this project on your machine. For example, with Docker or Homebrew or whatever. Downloading the Java jar, stuff like that, a bash launcher script. Anyhow, this is a tool that is very good in that you feed an open API specification into that tool, and then it will generate code for you for that API, so that you can then communicate with that API in a very natural way, very native to your programming language. Okay, so this tool can be configured to produce Java code, JavaScript code, Python, Go, C++, C#. Here under usage, this page will tell you, need to scroll down a bit to the generate section. There you will find an example of how to use that tool. So here they pass the command to generate code with the language Go, and yeah, they specify an output directory and the input YAML file. So for example, they use petstore YAML, which is yeah, really this YAML you see here. But yeah, this is pretty interesting, you know. This will then give you code that you can integrate into your projects, and then you can communicate with these web services as if they were some local thing on your machine. So you will have a very native feeling about the communication with this web service, you know. But you cannot only generate client code with such code generators. There are also code generators that will take an API file and generate server code, you know. So they will generate the server that will accept the HTTP requests, take the JSON objects, and then will pass the data to a function that you can define inside the API file here. This operation ID, for example, will then call the function find pets by status here on the find by status path. And yeah, then you only have to implement this function, and the whole communication, the whole server part of this can be automatically generated. And it even goes in the other way also. There are code generators that will take your code and generate such an API file so that you only have to implement this function. Then you run this code generator that generates an API file. Then you generate server and client code, and then you can give the client code to, I don't know, your customers or whoever. And yeah, you only have implemented this function, but like this, you can make this accessible through the net. But of course, if you make things accessible over the net, that's of course a security concern. So you need to look into authentication and stuff like that. And your function can even return an object, and this can be handled down here with these responses. So response 200 is again the status code, the HTTP status code for OK. And yeah, if this function is executed successfully, then it is supposed to return an object with a schema array whose items are pets. Okay, so that's again a rather object-oriented way of thinking about it. So your server will call this function. It should return an array of pets, and then this auto-generated server will encode that as JSON and send it to the client. And the client, if it's also auto-generated, might take that JSON object and turn it into an array of pets again. So like this, you can really pass objects back and forth between such web service servers and clients. Okay, I hope you can now see that for all this marketing buzzword stuff floating around in this cloud computing world, in the end, it's no witchcraft, right? You have these computers and they run services which communicate with each other through such an HTTP-based protocol. The machines over here execute containers, which is almost like virtual machines. The images are pulled from Docker Hub, mostly. You have some VPN stuff to limit the communication of these things. And many of these microservices, including Kubernetes, will offer you an open API specification for their HTTP-based communication. And that's at least a pretty good thing. You can run a code generator over such an open API specification. And so then you will have code to talk to these things directly in an object-oriented fashion, right? So within your programming language, you will have an interface as if you were talking to a local object, but this local object in the background does all this stuff with the HTTP communication, doing this in a manner that's specified by this open API. Okay, so I hope you have now a good, solid understanding of what is going on below the surface. As I said, I have never seen a good video about this topic, neither on YouTube, not even a pretty expensive Kubernetes tutorial that I've bought. So I hope that this has demystified a lot of things for you. And if you like this video, like it, share it, subscribe, and see you next time.